One of the foundational skills of Chapter 8 is being able to evaluate logarithms. When I think about evaluating, sometimes I think about simplifying the expression to make it less complex. Evaluating logarithms often will involve the use of log properties. So in number 1 here, we have a function f is the log base a of x, and we want to evaluate the logarithm at a few different places, starting with a. So a is my input. That's going to go into the argument. Whenever the argument and the base match, this will always equal 1. That's one of our log properties. To test it, we can always switch this into exponential form. Take the base of the log and move it over to the other side. The argument is left alone a. Base of the log becomes base of the exponent. We can see here that a is equal to a to the first power. In the second one, we have f of 1, so I'm going to plug 1 into the argument. Whenever the argument is 1, this will always simplify out to 0. Again, changing it into exponential form. 1 is equal to a to the 0th power. This is true. Anything to the 0th power will always equal 1. Next up, we have a to the 4th power, log base a of a to the 4th power. A couple different ways you could approach this. One way is to use the log property that allows you to take that multiplicity on the argument, that exponent, and move it out in front as a coefficient. That gives us 4 times log base a of a. Since log base a of a we said was 1, this is 4 times 1, which is 4. In the last one here, I have this function being evaluated at a cubed divided by a to the 6th power. I can simplify that before even plugging it in. A cubed is going to be our common factor here. Going to simplify this down to 1 over a cubed. So I get log base a of 1 over a cubed. Since it's a fraction in the argument, I know it's going to be negative. And for that base to get to a cubed, it needs to be raised to the 3rd power. So it's going to be negative 3. You can always check by switching it into exponential form. 1 over a to the 3rd power is equal to a to the negative 3rd power, which is a true statement. So our answers here are 1, 0, 4, and negative 3. Next are 2 examples of what I like to call nested logarithms, where you have a logarithm inside of something else. One property that is really helpful in these nested logarithms to look for is if you have an exponential expression where the exponent has a logarithm with the same base. Those are inverse operations. They're going to undo each other, and all we're going to be left with is the argument x. The key here is that the coefficient on the logarithm in the exponent needs to be 1. So taking a look at number 2 here, I see my base of 5 and an exponent of log base 5. I know those are going to undo each other, but before I can reverse those, I need to move that coefficient of 2 inside of the argument. So this is 5 raised to the power of log base 5 of x squared. Now these are going to simplify out, and I'm going to be left with just x squared. We can make this even more complicated by adding more layers to it. I'm going to work from the inside out. So I'm taking a look at this innermost expression. I see a very similar scenario. That logarithm in the exponent has a base of 10. So I see it's going to simplify out with the base 10 in the exponential expression. First, I got to move that 4 up to the exponent position inside the argument. So this is going to be 10 raised to the power of log base 10 of 2 to the 4th power, which these two are going to simplify out. They're going to undo each other, and we're going to be left with just 2 to the 4th power. So I have log base 1/2 of log base 2 of 2 to the 4th. I'm going to keep working from the inside out, taking this layer by layer. Now I have log base 2 of 2 to the 4th. I'm going to bring that 4 out in front as a coefficient. Log base 2 of 2 is just 1, so this is going to end up being 4 times 1. So I have log base 1/2 of 4. The last layer might be the trickiest of them all. When in doubt, you can always set a logarithm equal to x and solve for x. If I switch this into exponential form, I have 4 is equal to 1/2 to some power. Now, I know this needs to be negative, and I need to think about base 2. 2 to what power gives me 4? So 1/2 to the negative second power will give me 4, which means x is equal to negative 2. So that entire expression simplifies down to negative 2.